Hey, good morning. It's 8:15 and is about to get started. So, welcome to Core Simulation Laboratory course. And as promised in last semester in the fall, this is a course that we will take a bigger picture to field of simulation. So we will actually start looking at how is that we can apply the simulation in the different product processes. That's going to be the kind of like the main theme of this course. We do also some other matters. We also have a little bit of theoretical discussion in the beginning of the course, and once we're done with the theoretical discussion, then I'm going to invite quite a good number of visiting lecturers to give a little bit of broader picture of simulation that I'm able to produce by myself. Anyways, welcome to course, and my name is Aki Mikkola, as you may already know that. And I'm going to introduce, in the beginning, I'm going to introduce a little bit about the ground rules and the background of this course. And then a bit later today, we will jump to the real deal. And with that, let's get started. And based on the information provided by LUT administration, there's supposed to be was it 36 participants in this course. So that's a good crowd. And again, I apologize that this is a online lecture because this particular course is a more fun, way more fun when we do this face to face because this interaction is extremely important in this course. And we'll see if we're able to do so. At the moment, the instructions that I have received is such that there will be remote teaching at least until March something. I don't remember what day exactly in March, but let's hope that there is a chance that we can have face-to-face discussion beginning of the period number 4. Okay, so this course is really looking at this something that is called co-simulation or coupled simulation. And remember, this is a picture that I like a lot, and I introduced this picture to you a number of times in the course entitled Simulation of a Mechatronic Machine. And this course, we will make a deeper look to this picture, and we will actually start applying this picture to solve the real problems. And as you see, what is that I have in this picture is a kind of like representation of a typical product of a company in the field of mechanical engineering. This is a schematic representation in which we do have this conventional box, which is a mechanics here. This one here. Oh, I'm sorry, I have no drawing yet. This one here is of mechanics. It's very important to understand that the mechanics itself is not capable to make a machine because the machine is typically something that is capable to move. Mechanism, as it is a mechanism, would be something like a bridge, a building, so not really a machine. So what makes a difference between the bridge and the machine is an actuators. And we learned that there's a typical actuator, which is a hydraulic actuator. We're going to take a look at the hydraulics in this course too, but it could be pneumatics, electric drives, and others. But important thing is that these two boxes or disciplines, which is the mechanisms and actuators, they are coupled together. What we're doing in this course is we're learning to analyze the system where there's a different disciplines by using coupled simulation, or I think the more correctly technical term is a co-simulation, co-simulation, where these two boxes are solved one way or another, and they are, solved in a way that the information is shared between these two boxes, like it is shown in these arrows here. We will take a short look about the control schemes as well, the control systems. There is, again, discussion about the gamification real-time simulation, and that's the tool that allows us to take a user into account. And there's quite a bit of discussion about the working process itself, environmental models. That's important too, because if let's think about the heavy earth-moving machinery, and if you're analyzing the earth-moving machinery without having the earth or deformable ground, not making much of a sense to do that. So we're going to take a look at this box here, which is a working process. And so that's what's going to happen in this course. Now, moving on, teachers. Well, business as usual, so no differences. So it's going to be me and Suraj again. So I'm the one that is responsible of all the lectures, and again, Suraj is the one that is responsible of the guided tutorials. So you used to deal with this combination, so no difference this time. So the best way to contact us is to set an appointment via email, and my email address is either my last name, Mikkola, or it could be Mikkola at lut.fi, and Zura's email address is listed here. So these are the ways that you can communicate us, and I'm willing to have a face-to-face, well, not face-to-face meetings, but Teams meetings if there's something you wanted to discuss about related to this course or some other stuff. So I'm happy to do that as well. So again, me and Suraj. And I'm very happy to cooperate with Suraj. Uh, his YouTube channel is very famous, and he's the guy that knows this subject matter really well. So that's about it. Okay, why? Why this course? Why it makes sense to participate this course? Well, here are the three different categories, or three different answers to that question. First of all, like I say, we're going to look a little bit of the theoretical aspect. At this time, the theoretical aspect we're going to take a look at is twofolded. So we, first of all, we'll take a look about how is that we can model spatial bodies, three-dimensional bodies. And that's a concept of modeling three-dimensional bodies is a little different than modeling planar bodies. And I would like to highlight that the differences between the planar and spatial cases. We're not going to repeat all these details, what we did in a fall, like how are all the Lagrange multipliers and so on and so forth. No, that's not the plan here, but mainly about what is the difference in terms of kinematics. What is needed to model spatial bodies? And of course, that the major difference is related to description of rotations, because in planar case, a body can rotate in a one way only, whereas in a spatial case, body can rotate in a three different ways. And surprisingly enough, these rotations in a three different ways is mathematically very cumbersome to describe. What are the ways we can describe it? That's what I will explain in the very beginning, getting started from today. And then another much bigger subject matter is modeling of flexible bodies. Every now and then there's a need to describe deformable bodies, bodies that are capable to deform due to the forces. This is typically because description of deformable bodies makes models to be more accurate. Sometimes it's not acceptable to use this assumption of rigid bodies. And this is not acceptable because the results are not occurring with reality. And in those cases, it's necessary to describe flexible bodies. And we will learn most often used technique. I provided a like half an hour highlight on that subject matter in a course, full course, but this time it's going to be way more thorough discussion. So we're going to look like how exactly we can describe the deformable bodies. What are the limitations, and what makes sense and what not makes sense. Now this is a discussion that is a little bit lengthy because I would like to get started from method called finite element method. And some of you may be already familiar with the finite element method, but that's okay because the way I'm explaining the finite element method is probably a little different that you're used to deal with. And then another thing is that I really want to put a lot of effort to you to have an understanding about relation between the simulation models and reality. And this is important because there is no such simulation model that represents the reality one-to-one. That's not just a little bit of medication against something that is not really a listed medical condition, but it's a severe condition, which is called simulation disease. The simulation disease, as I probably explained to you in the fall, is a disease that you do no thinking anymore, but you're relying on just simulation, nothing else but the simulation. And the best way to get the protection against that medical condition called simulation disease is to learn a critical thinking against, yeah, you're right, against, I say against computer simulation. So even though that we do hear computer simulation and I'm an advocate of computer simulation, still I wanted you to learn the critical thinking against computer simulation. Why? Because a master level student, you should have an objective view, not just a heavily biased towards simulation or heavily biased against the simulation, but an objective view. And that's something that I wanted to teach you as well. Then there's got to be not just the multibody system dynamics we're touching in this course, but others too. And I would like you to learn different methods, a little bit about how is a palette of computer tools that is currently available, and not just the big picture of the computer-aided tools, but also a little bit about the different sub-methods within these tools. And it will be, again, very important to understand the limitations and advantages related to different numerical approaches. And that's definitely something we do. And then applications. Vehicle modeling. It's a little bit unclear what kind of vehicle we're gonna do in this course. I can see that I have problem in my YouTube studio. It says that I'm not receiving enough video maintain smooth streaming. What? Why? Because I should have a fairly strong connection here. The problem is still there, and I can see my picture is a bit blurred, and now is again excellent connection. All right, so vehicle modeling, what kind of vehicles we can touch, that's a little bit unclear at this time. Contact modeling, finite element method, like I said earlier, biomechanics, and that kind of things. So those are more like, finite element method is a method itself, but contact modeling can be considered as a sub-theory under the multibody system dynamics, but vehicle modeling is clearly an application field. We're going to take a look at the other application field as well. And most of them are explained by visitors. So I hope that there's going to be a lot of fun, and I hope there's going to be a good visitors that you can learn a lot from those visitors. Okay, so moving on. As this course is entitled laboratory course, which implies that there is something practical in this course. And something practical will come from those visiting lectures, but it also will come from one simulation work. Now we're going to learn a little bit about how is it we can design a control algorithm for hydraulically driven crane. There's going to be a flexibly described mechanism. The mechanism where there are deformable bodies. And we're going to look a little bit about the model verification. So we are comparing your simulation models against measurements. And then eventually we can build a control algorithm that shows a little bit about what is it you can do what additional aspect you can do with help of simulation. So that what follows a bit later, and this work will be carried out in a guided tutorials, and guided tutorials will get started not this week but next week. And again, Suraj is the one that is responsible of that. Okay, here are these technical aspects or content of lectures, and like I said, there are these two theoretical things that I would like to explain. First is this three-dimensional kinematics. I'm calling that very like sophisticated way, like three-dimensional multibody dynamics. Not really multibody dynamics because I'm focusing on kinematics and rotations, which is valid whatever you do. Even when you do the gaming drawings or any kind of spatial visualization animation, it's good to be aware of this, how is that the bodies can be described in three-dimensional space, and how is that rotations can be described. And once we're done with this three-dimensional kinematics, I'm going to explain also a little bit about the robot kinematics, which you may be familiar with already, but it goes so close to that field. So I would like to offer a short explanation about how is a relation between the kind of like multibody kinematics and kinematics often used in a robotics. And then we're going to move on to describe about flexible multibody dynamics. And there's one lecture that is dedicated for the theory of finite element method. So I will get started from very fundamentals. So we're going to discuss about shape functions, which is like a soul of a finite element. We're going to look a little bit about how is a polynomial expansion that is needed to build the shape functions. We're going to look a little bit about how is the selection of polynomial expansion, or how that will affect the accuracy of finite element method. A little bit about how is that you can do the dynamics with help of finite element method. And then we're going to move on to another space. If finite element method is all about to describe the nodal positions and nodal displacement, then we're going to move on to another space, which is a model. So we're moving from nodal to modal space. And in that, we're going to take a look a little bit about eigenvalue analysis. And that gives us a possibility to introduce a technique that is called modal reduction technique. And that's going to be very interesting. So it's kind of summarizing the information that you have learned from vibration. I'm not sure if there's a course entitled vibration. Well, depending on your home university. I mean, the university you received your bachelor degree. I'm sure you are familiar with the vibration in certain level. So we're going to take a look at the vibration because the eigenvalue analysis is about explaining these vibration properties of a structure. And then this modal reduction, which is extremely important to know when you're moving on to use this opponent scores entitled massing dynamics. And then there's a midterm exam. And you see that, what happens here is the first 6 weeks is about the theoretical explanation. Yeah, but I would like to put it in a way that there is not just, equation after equation after equation, but more like, okay, what they represent for us. And why is that it's good to be aware of these things? And I would like to collect an information from surrounding disciplines. So that's the way that once you're done with this course, you have broad perspective about the computational methods. Okay, midterm exam is after week 8. How? I don't know. I need to figure that out. Maybe it's gonna be model exam. Honestly I don't know at the moment. So, but we still what is it, like 6 weeks away from that. So there's plenty of time to figure it out. But I kind of doubt that it's a conventional paper exam. I doubt. But again, as we proceed in this course, I will let you know how is that the practice related to midterm exam. Okay, then continuing from that, then there is a visiting lecture about the vehicle modeling. Then there's going to be something related to fatigue, and there is a visiting lecture about about the biomechanics, visiting lecture about gamification. We also look a little bit about the large deformation contact modeling, and again, midterm exam. That's going to be already, April, I think. Again, very much unclear how is it we can organize that, but we will figure that out. All right, so tutorials. So we will get started from 3D mechanics. There's a little bit of hydraulics. There's a little bit about the flexible bodies. And I will go fast because this is a business of Suraj more than mine. And then we look a little bit about the control algorithms, the reporting, and so on and so forth. And the instructions will be available as soon as Suraj will organize the first guided tutorial. And that's going to be next week. All right. How to pass the course? What are the important ingredients or components to pass the course. 2 components, equally important. Equally important. So this is important to keep in mind. So it's not just enough to do the written exam, or not just enough to do the simulation work, but you have to do both. And they are, like mentioned, equally important. So accepted simulation work, accepted written exam, and the final grade will be computed such the way that is average from simulation work and written examination. So simulation work plus written examination divided by 2, that's the way to go. You can upgrade your final grading by doing in-class quizzes. And you know, the in-class quizzes is business as usual, so there's no differences comparing how it was in fall time. So I'm going to have questions related to material that I'm explaining. And if you're able to answer those questions correctly, you can get some extra point. And this time, the maximum extra point is a 0.5. So meaning, let's just do a hypothetical computing here. And again, what happened today was that I forgot my pen to my university office. Now I'm here in my basement office, so I don't have a pen with me. But let's take a look about hypothetically how the final grading could be. All right. So you're scoring from simulation work, you're scoring, let's say 2. Okay. From written examination, you're scoring 3. So that's going to be 5 divided by 2, going to be 2.5. And we always are in your side because we would like you to do well. So it's going to be rounded up. So it's going to be 3. And then you do these in-class quizzes. So it's going to be 3.5, which will be rounded up. So it's going to be 4. So final grade will be 4. Even though that your simulation work is worth of 2 and your written exam is worth of 3, you can still score 4 out of 5 in this course. 4 out of 5 is outstanding. It's awesomely good. And now I know that there are always a bunch of students that, yeah, the only way that you are happy is that you're scoring 5 out of 5. So how that could then go? It could go such the way that you're doing a good simulation work, so it's not 2, but instead it's 4. So it's going to be then 3.5. So this is going to be 4, and you do your in-class quizzes, so the final grading will be 5. So hypothetically, that's how it goes. But again, please understand that 3 out of 5 is considered as good. And I don't know how is your wording, but good for me is good. And that's something that you can be proud of yourself. Again, I got the Nero in my YouTube studio. Let me know, by the way, using the chat window if you have difficulties to follow my streaming today. I did not receive this kind of error message in my university office, but it says that the streaming is not smooth. Don't know. But I got no comments so far. So I guess it is okay. So, like promised, well, actually I promised already one of the participants that what I will do during the weekend, which was already last weekend, is that I'm going to make one video about the career counseling. So this course, I really want to discuss about other matters than just, how is a finite element modeling and how is a contact modeling. I would like to keep my perspective to you regarding the, not really, I cannot say life. I cannot teach you in that, but I can teach you things related to career counseling. And for some reason, which I cannot explain it to you, I feel that this career counseling is something that I'm taking very personally. So I'm gonna, I don't know, maybe it's gonna be next week Monday that maybe that's the best way to go. So right after lecture, there's going to be a supplementary lecture, which is a career counseling. And again, it's going to be one of these YouTube recordings or streamings, but still you can get a little bit of an idea, how I feel about career counseling. And I would, for international students, it may be good to follow that lecture because I'm trying to explain you what are the ways you can find your way to Finnish industry. And for Finnish students, well, it's not hurting to know that my reasoning in that regard. And also those of you that are thinking career in academia, I will explain what is the name of the game in academia. So, so maybe the best way to go is that next week, Monday, I'm going to make a reservation for an additional lecture, and that could be, let's say, 45 minutes. And that 45 minutes is about the career counseling. So sorry that I haven't had time to make this recording before. Okay. And what I see here in my YouTube studio is that I got the one extra like. So I guess that you like that idea. That's the way that I'm interpreting your reaction, because there is no other reaction here. Again, I made this streaming such the way that if you give me a comment, this comment is not visible afterwards when somebody's checking out the recording. So please feel free to comment. At least that's what I was thinking when I made this scheduling for today's lecture. And I'm slow. Okay, in-class quizzes, no surprising here. Oh, I see that the likes are getting up, so it's going to be 5 likes already. So the career counseling, definitely. And I'm also thinking about, at least we will get started from the career counseling. Maybe there are other matters other than the technical matters that I can help you. So those are the ones that I will also try to put you a little bit extra supplementary material. And I can give you actually a link to one of my previously made YouTube recordings about how to make a good publication. I mean, you guys may not be interested about how you can make a good, high quality journal publication, but making a good journal publication and making a good master level dissertation work, they're very much alike. So in that perspective, you may learn a lot from those recordings. So that too, next week, Monday, right after this more theoretical and a bit more boring explanations. Okay, in-class quizzes, a total of 25 points available. And again, I'm not expecting you to score 25 points, but if you can do 14 out of 25, so then you're going to get this extra 0.5. And this is a little bit of black and white. So you scoring less than that, you get nothing. And you scoring more than that, you will get this 0.5, and that automatically gives you 1 extra point to your final grading. So that's how it goes. And those of you that are not familiar with my teaching style, which I hope that each of you are already familiar with my teaching style, you can answer the in-class quizzes by logging to Socrative. And the way you can log in is by using your student ID number. So you need to know your student ID number. And yeah, that's it. That's how it works. Okay, so we made your life enjoyable in a way that we introduced something called mid-reports. So we are not expecting you to do the simulation work in such the way that you get started sometimes in period number 4, and then within a week or two you rush yourself and try to complete everything. No, what we did instead is that we wanted you to get started next week, and we are forcing you to make a mid-reports. And if you're missing mid-reports, and the mid-report is something that we want to see basically that you're still alive and you're making your efforts. But if you miss them, we're going to take some points off from your simulation assignment. So if you miss the 1 deadline, we're going to take 0.5 points off. You miss 2 deadlines, it's going to be 1 point off, and so on and so forth. So you can do the math. So if you miss all of them, well, you know that your maximum score is no longer 5, but it's just seriously reduced. These are the deadlines. And again, Suraj will explain the details. So if you miss all of these mid-reports, so we will take 1.5 away from your maximum. So it meaning that your maximum is going to be 3. So that's going to be very unfortunate. So don't do that. So don't do it, because basically it's not so much we're expecting you to do, but we would like to teach you a style that, it really makes sense to do the reporting during the course of of the simulation work. While the simulation work is developing, it really is a good idea to start doing the reporting as well. Okay, so with that, so previous knowledge. No really previous knowledge, but definitely helps if you have made your effort to complete the simulation of a mechatronic machine, because we're going to get started from multibody. And if you're not familiar with this is going to be a little bit of rocky road in the beginning. And then later when we're looking at these applications, so it's going to be okay. But again, recommendation is that you have simulation of mechatronic machine, or you have made an attempt to complete it. Literature available, you see that there is already lecture notes. Part 1 available in a Moodle database. There is a PowerPoint presentations like the one that I'm introducing today. This will be in a Moodle database momentarily. I mean, right after today's lecture. Then there's a book made by my former supervisor, Ahmed Shabana. This book is an awesome book, of course. It's a great book, but it's not so easy to follow. It's not, I mean, that it kind of requires to be somewhat deep prior understanding on multi-body system dynamics. But if you want, you can take a look. I think we have plenty of copies in the library, so you can borrow one and you can see how well you understand that. So dynamics of multi-body system, chapters 5 and 6. And chapters 5 and 6 are explaining how is a flexible multi-body dynamics. But again, it's not really mandatory. So I'm offering everything here in my lectures and in other material that will be available in the Moodle database. And one clear difference between this course and the course that was in fall is that when we're moving on to new subject matter, I will give you a list of possible questions. And in written exam, I will stick in that list. So I'm not going to add any additional questions. So those are the questions that I will select to be in written exam. So you will see that momentarily. But once I get started, let's say, okay, now we're going to discuss about three-dimensional kinematics. I will give you a list of possible questions. And then within this, once you know the answer for those questions, then you're done. Then this is the only thing you need to know. And also I will give you an opportunity to select one question out of the many that will be in the exam paper for 100% certainty, that for sure it will be there. So you can be sure that if I will definitely ask that. And then there's also a possibility that you can vote one question off. So if there's something that you feel that this is overwhelmingly difficult, I've been reading over and over again, but still I don't get it, you can vote it off. So you have this power to do so. And this voting will be right before the midterm exam. Again, you will see the style, you will see the voting once we proceed in the course. All right. Okay, so introduction, what I will learn in this course. So a little bit about things we do in this course. And the first thing is this extremely important, this co-simulation. So you're going to learn to combine different disciplines. Multi-body system dynamics, finite element modeling, hydraulics, control algorithms, even CAD drawings, contact modeling, so on and so forth. You're capable to put them in one package that is representing a machine and its environment. Sometimes even user is involved. But we're kind of looking at the big picture, not just looking at, okay, how is the detail of a structure using a finite element model, but more like how is it we can make the finite element model to be in a form that we can use that in other disciplines, multi-body system dynamics, hydraulic modeling. So this is what we really wanted to do here. So most important thing, co-simulation or couple simulation. Sometimes a bit confusingly, I'm calling this couple simulation, but what I do mean is a co-simulation. Co-simulation that, information is transferred from one discipline to another. So that's, by the way, very much in fashion at the moment. And some of the companies that are making commercial software, they sometimes don't call it as a couple simulation or co-simulation, but or simulation of multiphysics. Multiphysics is sometimes used, meaning that again we are combining different disciplines together. So that. All right, and then moving on. Then we're gonna take a look about this description of flexibility, and we're gonna stick the methods that are most often used. And those are kind of pleasant methods because they keeps you kind of broadening your perspective regarding the vibration and gives you a better understanding about what the machine or what the vibration stands for. What is a physical interpretation of vibration? And then we can also look about the applications. And once I find my way here, okay, I need to do this. So this is a cable modeling. So we'll look at the different kind of flexible bodies, conventional flexible bodies, which is typically like part of the crane arms or arms of other structures. But we also take a look about the cable modeling, like shown here. Another kind of like special features, even the biomechanical things, if we have a time to do so. So this is a cable modeling, and you can see this is a cable model that there's even this without string effect. That effect means that, you know, if there's a cable without any pretension, it's on the transverse vibration is very low. Once you turn it down, then it's that the frequency will change. This is what you can see when if you play a guitar, you can tune the wires, and this is the way you can make them sound in a particular way. And this you can see also in the cranes and well in the cables in general. So we will look at this kind of stuff. Okay, and then a little bit about how is an extension of simulation to fatigue. How is it we can possibly use our advanced simulation as a part of the fatigue design? And why is this? Well, again, I'm not 100% sure, but it's my understanding that you know, in LUT, Department of Mechanical Engineering, have a special feature in the welding and fatigue structure. So I would like to give a support to this fatigue and welded structure by explaining what is that we can do in the field of simulation to provide additional information for the need of fatigue analysis, and how is it we can, you know, learn a little bit about, you know, what's the typical phenomena on the welded structure in terms of fatigue. Maybe you're already familiar with that, but doesn't hurt to replace or repeat that one more time. Then we look a little bit about the contact modeling, and in contact modeling we are checking out the different applications. That's like bearing modeling. We will we'll look at the cames as well. How is the contacts are described in the cames. By the way, this is a ball bearing model with no, I mean, this ideal model. So there's no oval inner shape or anything like that. There's no fatigue fracture or anything like that. But you can see even when you had a ball bearing like shown here, reaction forces. I don't know if you see this clear, but there's a short shaft here, and then there is a force hanging end of the short shaft, and you can see that the reaction force here is a fluctuating. And why that is fluctuating is because of the nature of the ball bearing. Because ball bearing, the stiffness depends on how is the ball positioned. So if you have one ball where the force can travel through the ball, the stiffness is different when there's two balls and the force is traveling via these two balls. I don't know if you can understand that from my hands, but no worries if you don't, because we will get back to that. But again, just an example about the contact modeling. And that's it. That was the last slide about the introduction. And now is 5 minutes to 9 o'clock. And I was thinking that no breaks today. I don't know if you like this. If you want, we can have a short break and then continue. But I was thinking that we have no breaks and we will just continue here. And then we close today at 9:45, roughly 9:45. That would be my plan. And I don't know, this is a rough start, Monday morning, 8:15, and it's me. So not the pleasant start, but if it is okay to you. And again, I see no comments. I don't know what's wrong with you guys. So you don't want to communicate with me today. Like I say, your comments will not be visible later in a recording. But my question to you: would you like to have a break, or you're okay to just go with no breaks? Or is it my settings incorrect because I don't see any comments? I don't know. I guess that is correct. So we go no. I don't know how to interpret your unwillingness to communicate with me, but I'm thinking that means that yeah, we can go and have no breaks. Okay. Maybe somebody can send a message to just to ensure that you still. I know that you're alive because there is this 8 likes, so it's okay. All right. So 3D multibody dynamics. That's where we're gonna get started. And soon there's in-class quiz. So make sure that you have your mobile phone ready or your browser ready. So we momentarily will open the Soccer and this is gonna be my first in-class quiz. Okay. So what we're going to do in three-dimensional multibody dynamics, here's a list of topics. So we will get started from introduction and then description of particle. And yes, there's going to be this rotation of particle, and I'm going to explain that. You remember, this is the same that the Santa Claus, so the rotation of the particle is non-existing. So particle don't have these rotational degrees of freedom. And then we're going to look at how is it the way we can describe the orientation and rotation of coordinate systems. So we look at the method you're already familiar with. So we will take a look at the Euler angles. And this time we're going to look at what is the problem related to Euler angles. And the problem is singularity. And what that means, what it means. That I will explain you a bit later. And we're going to familiarize ourselves to Gimbal Locking. And that's going to be definitely something that you need to make sure you know what is a Gimbal Locking. And then because there is a problem in Euler angles and all the methods that are based on 3 rotations, we can introduce a method that is based on 4 parameters. 4 parameters to describe rotations. And this is confusing. Like, what? 4 parameters. So is it meaning that there's a 4 way that the body can rotate? No, there's no 4 ways that the body can rotate. But there's still 4 parameters that is used mathematically to describe the body rotations or coordinate rotation. Maybe put it better to put it this way. And the first method we're going to learn, which is based on 4 parameters, is a Rodriguez equation. An extension of Rodriguez equation is Euler parameters. Euler angles and Euler parameters are very different. They are not cousins. They have no relation. I mean, other than the name relation. Euler is a common thing. But concept-wise, they have no relation. Shortly, we're going to take a look about the properties of rotation matrix and robot kinematics. That's something that is a little bit extra material, and that's going to be next week. So, as I promised, every single time we're moving on to new subject matter, there's a list of possible questions. And again, it is these questions only, nothing else. So I'm not allowed, if you agree with my rules, I'm not allowed to add any additional questions to this list, but it's just going to be this list of questions. So it's going to be like, what kind of system can be analyzed using the multibody system dynamics? You already know that. But just to kind of like give you an extra boost to listen my talks, here are the questions. Maybe what you can do this time is that you can take a screenshot. You can take a copy of this list. Of course, this list will be available later available in a Moodle database. But if you now want to take a list of this, you want to take a copy of the list, take a screenshot, and then while I'm explaining these as different subject matters, then you can kind of put in writing the possible ways you can answer those questions. So, and that's it. So the questions are like, explain the concept of Euler angles. Well, probably you already know that. Explain the Gimbal Locking. Probably you do not know that. And then explain the concept of Rodriguez equation and so on and so forth. How is a 4 by 4 matrix representation, or how 4 by 4 matrix representation can be used in robot kinematics. So this is stuff, and this is how it goes. So 11 questions. And now what we're going to do, like item by item, we will go through these questions. Getting started. 3D multibody. And I was just checking, like, do we have any communication here? Do we have any comments, any questions? I see no comments, no questions. But this is the way it goes. And again, like I said, you have this opportunity to vote out one question. So if there is something that you definitely don't understand, so this is so difficult, so cumbersome that there's no way that I can familiarize myself with this answer of that question. So vote it out, vote it out. And if there's something you love big time, yeah, you have this opportunity to ensure that that particular question is in the exam paper. So simple game. 3D multibody dynamics, so kind of like introduction to multibody dynamics one more time, because it's important to be aware what this multibody system dynamics is designed for and what is that is capable to do. The questions are here. So what kind of system can be analyzed using the multibody system dynamics? What couple simulation means? Why rotations, well, you see that there is even typing mistake here. Why rotations are more difficult in the spatial than planar case. So let's get started here. And this is refreshing your mind from the simulation of a mechatronic machine course. Now remember that the multibody system dynamics is designed for a system that consists of multiple bodies. That's where the name is coming from. Multi-body. So multiple bodies. What is a multiple body? So it's going to be one or more moving bodies. So even if you have one body, you can still analyze it by using a multi-body system dynamics, even though the multi kind of reflects that there is a more than a one bodies. Of course, if you have more than a one bodies, the method is going to be more powerful. But we learned that there's like this kind of symbol pendulums and other symbol mechanisms that sure you can analyze by using this method. But if you have more bodies, then again, it's going to be systematic approach where no thinking is needed. You just take one step at a time, and what you're going to get as a result of those steps is equations of motion. No thinking needed. Beautiful method. It's like a finite element method where no thinking is needed either. More thinking is needed in a finite element method than in a multi-body system dynamics. Okay, so multiple bodies. And the special thing about multiple bodies is that the bodies are connected together via joints. So that's what makes a multi-body system dynamics. And a good example is this crankshaft. And let's see how well that I'm capable to draw the crankshaft using my hand, my finger here. So it could be crankshaft, connection rod, and a piston. Sorry that this is a little bit unclear drawing, but we have here three bodies that are connected together via revolute joint. So this is connected to ground by a revolute joint. These two bodies are connected together via revolute joint. Connection rod and a piston are connected via revolute joint. And then there's a translational joint between the piston and the ground. So there are joints. Joint connections is something that is making a system as a multi-body system. Now, in multi-body system dynamics, we do not make any assumption regarding the magnitude of rotation. Crankshaft is here as an example, this body here. So that when the piston is moving back and forth, crankshaft is rotating around this point here. And that's okay, because we're using trigonometric functions in a kinematics. So those are nonlinear functions, so we can easily describe the nonlinear kinematics. So we are not making any assumption regarding the magnitude of rotation. So that's another special feature of multibody system dynamics. And I mentioned already that no thinking is needed, no intuition is needed. So you just follow the steps and you get an equation of motion. That's it. And it can be applied to robotics, mechanisms, vehicles, and different kind of machines. So this is explaining what is a multibody system dynamics, or let me see, what kind of system can be analyzed by using a multibody system dynamics. System with multiple bodies, where the bodies are connected together via joints. And no limitations, no assumptions are made regarding the magnitude of rotation. That's it. All right. What the couple simulation means, that's going to be a bit later. Let me see, what was the third question? Why rotations are more difficult in spatial and planar case? Now, we learned a little bit about how is a spatial case in simulation of a mechatronic machine, but now we're going to learn more. In three-dimensional space, it's kind of an extension from a planar case, kind of. Well, only kind of. And why only kind of? Because, as can be seen here, I'm just adding one more axis to my coordinate system. So I'm used to deal with the x and y axis. And now I'm adding one more axis with this z axis here. And that's when looking at the translation, that's pretty much what it is. So it's one extra dimension in terms of translations. But in the terms of rotation, things is very different then. Because in a planar case, the body can rotate only around the z-axis, which is non-existing axis in a planar case. Whereas in a three-dimensional space, it can rotate in a three different ways. So 3 different ways. And that's something that is making description of rotations way more difficult. There are several reasons for that. Because first of all, if you're describing your rotations using 3 parameters, which kind of is the first obvious selection, you have 3 different ways using 3 parameters. Whatever using 3 parameters, you have a problem. And the problem is singularity, or capability, or not capable to describe rotations as independent rotations. There is always this possible configuration that these 3 rotations are no longer clear, and is not clear what is what. And this is when you're reaching the singularity or locking configuration. You cannot differentiate, what rotation is what. That's what can happen to you. And it's always a problem whatever using 3 parameters. So that's a big problem. And that's already tells how much the rotation description is different in terms of planar and spatial case. So usual way to solve the problem is adding one more parameter. But now things are ugly because, we have 4 parameters, but the body can only rotate in 3 different ways. So what is this? So 3 different ways and the 4 parameters. You see they don't match. There's no way that they can match. So we have to force them to match. How is it we can force them to match? Well, if we could force them to match by introducing constraint for these 4 parameters. And now because of the constraint, they can be describing 4 different rotations, 3 different rotations. But again, it's going to be the details that I will explain this week and will continue next week. So that's why it is different then. Okay. Now, another thing. So the mathematical description is something that is a bit of the problem. Another thing is that order of rotation is something that is very important. You cannot change the order of rotation in 3-dimensional space. So in 2-dimensional space, you can play as you want. But in 3-dimensional space, you cannot. Because the order of rotation is very, very important. So that's another thing that makes it a bit difficult. And now comes something that you definitely are not going to understand me. But still I'm going to say that. Because this is another mathematical problem. But something that is very important to understand. And we will understand this eventually. But remember when we were discussing about planar space, we say that the coordinate that was used to describe the orientation was theta. And then we say that, okay, angular velocity is theta dot, like this, theta dot. And this was the same than angular velocity. Yes, it is. That's the case in planar case. But in a three-dimensional space, this one here is a vector. Is a vector that consists of 3 or 4 parameters. 3 parameters if we're selecting to use a 3 rotational parameters like Euler angles. 4 parameters if we're going to use something that is not suffering from singularity. So this is a vector, not the scalar component. This one here is a vector as well. So this angular velocity with respect to global or local coordinate system is a vector, which consists of 3 components. And these two things are not the same anymore. So they are not the same anymore. And that's another headache. You can force them to be, I mean, that there's of course the way you can link them to be equal, but you have to do this linking. So they're not automatically same, and they're never actually same. So there's no way to select this kind of a rotational or set of rotational parameters that they will be equal. That's not going to happen to you. It's not going to happen to any one of us. So that's not possible. But you can introduce one additional component to build the link, a bridge between these two components. What is this bridge? Well, we're going to learn that a bit later, but that's for your information this time. Okay, and moving on. By the way, I'm still a little bit worried about this, your inability to not to make a comment. Is it so that my streaming settings are made such the way that there's no way to make a comment? I really don't know. It could be. Could be. I'm a little bit reluctant to check my emails, but we'll take a look at that later. And I need to check like if I have made my streaming settings incorrectly such the way that you guys cannot communicate with me. Well, anyways, moving on. Co-simulation. We discussed about the co-simulation already, or couple simulation. It basically means that we're putting different disciplines together. In practice, it means that we're putting different softwares together. Softwares are communicating. Like the software that is specialized to finite element modeling is communicating with the software that is specialized to multibody system dynamics. That is then is communicating together with the software that is specialized to actuator modeling, so on and so forth. And then there could be even one more software that is specialized to visualization. Maybe this kind of setting could be used. But the coupled simulation is simply combining different disciplines together. So that's how it goes. Now moving on. So description of a particle. And this is again something that you for sure you know this really, really well. So description of particle goes such the way that we're gonna introduce additional coordinate system, which is called body coordinate system, to be able to describe the particle position with respect to global coordinate system. Again, remember our ultimate goal here is to describe particle with respect to global coordinate system. And easiest way to make it happen is by introducing additional assisting coordinate system, which is traveling and rotating with the body. And this additional assisting coordinate system is attached to body and is called body reference coordinate system, body coordinate system, if we can give a nickname to this coordinate system. What's the benefit of this body coordinate system? The benefit is the fact that within this coordinate system, particle position remains to be constant within this coordinate system. So it's only within here. And this is when we are assuming body to be rigid. And if it is not rigid, then even that assumption is no longer valid. So what we do then is that we have this body reference coordinate system, and now using the body reference coordinate system, we can use a vector u-bar that scans every single location within this body, vector u-bar here, this one here. And when it is scanning every single location within this body, we can take all the particles into account. And then what we need to do then is that we need to map body reference coordinate system and the global coordinate system together. So we have to find a way that one coordinate system maps to another. And this can be carried out in practice by using this rotation matrix, 3 by 3 rotation matrix. How? Well, that's what we're going to learn very soon. So we can use these Euler angles, we can use another techniques, but we have to have this mapping, so which is converting the representation to one coordinate system, then another coordinate system. Then we have one more component here, and that's the component that is taking translations into account. So first, we introduce a body reference coordinate system. With help of body reference coordinate system, we can introduce a vector u-bar that is scanning every single particle within the boundaries of the body. And then we mapping the body reference coordinate system to global coordinate system with help of 3 by 3 rotation matrix. And then that can be added to description of translation, and the translation description is this vector R. This is a business as usual. No surprises here. The dimensions is the only difference. Now we're gonna take a look at the first methods. So the first one is Euler angles, and I think today we also have a time to look at the the Rodriguez equations as well. Euler parameters, I'm not sure about that, but then what time it is? So it's 9:17. We'll see. Three-dimensional multibody dynamics. Explain the concept of Euler angles. Explain the Gimbal locking. All right. Those are our targets. So let's get started from the Euler angles, which I'm sure you guys already know that. And again, because I'm missing my pen, I might have a little bit of difficulties to use my hand to explain this properly. But again, Euler angles is based on the concept of successive rotations. Successive rotations means one rotation after another. So it goes such the way that you have first, in the beginning, you have two coordinate systems that are parallel to each other. So two coordinate systems where there's no difference in terms of translation and a rotation. You put them parallel. Then you can introduce a rotation, which, oh my God, again, these weird letters, phi, psi. No, this is psi. Yeah, I know. One of you guys emailed me an explanation about how to pronounce these notations, but it's no longer in my head. I think that this is psi. Well, anyways, you see this one here. So psi, let's just call it psi. So you can introduce amount of rotation that is psi around the z coordinate axis. And what's the consequence of that? Now these two coordinate systems are no longer parallel, but the one coordinate system is rotated as it is shown in this picture here. All right. Then comes the role of successive rotations. And in a successive rotation, you will take a hold of once rotated coordinate system. At this time, you're rotating the once rotated coordinate system around the axis x. And the amount of rotation is theta. Now you have 2 times rotated coordinate system. And then one more rotation, you again will take a hold of z coordinate axis. You rotated 2 times rotated coordinate system by z axis, and that rotation will be phi. Well, you read it by yourself. You see this clearly from the picture. And this is going to be our third rotation, like shown here. And now what we're going to do here is that we will have a mathematical representation for each of these pieces, or each of these components, let's put it this way. And remember how we did the rotations in a planar case? We were using 2 by 2 rotation matrix. And you see that this sub matrix, which is describing planar rotation, can be seen here. So this is the one that is describing planar rotation. And you see that this column here is representing where the rotation takes place, z-coordinate axis. This is a column that explains where the rotation takes place. And here is again 2 by 2 planar rotation matrix. And here again is where the rotation takes place, 2 by 2 rotation matrix. Now, mathematically, successive rotations can be described by multiplying these piece of rotations together, or these sub-rotations together. This is how it eventually will look like. And again, for sure, I'm not going to ask you anything like, okay, derive me this matrix. For sure not. But more like concept behind of this. Now, here's the final 3 by 3 rotation matrix. And this final 3 by 3 rotation matrix is based on 3 parameters. And these parameters are the ones that I'm unable to read correctly, but let's call it psi, theta, phi. Or was it the other way around? Anyways, these are the 3 parameters. 3 parameters. 3 rotations, 3 parameters. All right? Where these parameters are typically coming from? Well, you see that there is this gyro zone here. So my explanation is typically because these are used in a gyro as well. So they are like z-coordinate axis, x-coordinate axis, and z-coordinate axis. So this is where they could come from. This is very often used as sequence of rotation. Sometimes you can see some difference, but again, doesn't really make much of a difference in terms of mathematics. So whatever using 3 parameters, you have this mathematical difficulty that is associated to singularity. Now, let me see. Okay, I got the message, but it wasn't communication through the YouTube studio. I seriously think that maybe I made a mistake in my settings such the way that you guys are unable to make a comment. I'm able to make a comment. Yeah, I can do it. But I take it you guys cannot. Okay. All right, so here's things I'll put it in writing, but this is what I already explained to you. So singularity is always a problem if body rotation is described by 3 parameters. In Euler angles, the singularity is due to the fact that rotations are not necessarily independent. And as you see in this one here, if the first angle and the third angle, they might have a same axis. They might have a axis aligned. And when the axis is aligned, then you're losing capability to describe spatial orientation or spatial rotation because your 2 axes are no longer different, but they're same. And this means that there is this locking, which is, this gimbal locking, which we will take a look at the animations momentarily, or I'm going to offer you more link that you can familiarize yourself to gimbal locking. This gimbal locking is not a mechanical lock. It's not like, this gyrus that is shown here, this upper right corner, is not really locked in a way that it's no longer capable to move. It doesn't mean that, but it means inability to describe difference between 2 rotations or 2 angles. And this is something that can have some serious difficulties. It's a difficulty in you will see in the videos that are listed here that there's a difficulty in aerospace applications, and it's explaining a little bit about was it Apollo 13 or something like that, and this 8-ball, how the 8-ball is used to describe the orientation. So take a look at those stories, and they're kind of funny stories. But keep in mind that the gimbal locking is an inability to describe rotation because 2 axes becomes to be parallel. That's the problem. How you can get rid of that? Well, you cannot get rid of that. You always have this problem whenever you're using 3 parameters. So there's no way avoid it. So I'm planning not to play these videos, and but instead I will. I think that let me see how it will work if I will play these videos. would it be something that you see you will hear the audio? Oh, look at that. So it's easy decision because not willing to play to me. Okay. All right. Particularly this lady explaining airspace application, which is worth a take a look. Worth a take a look. And what I will do then is that, oh, I see, now I know why I'm unable to play, because I was in a drawing mode. So I will put these links to my YouTube chat window so you guys can just simply copy paste that. So no need to type these links from this PowerPoint presentation, and just another one, this one here. There you go. Again, like I say, I'm not going to play these videos to you. You take a look at by yourself, and they're very much self-explaining. And we will get back to this topic next week, Monday. And that's when we're going to kind of summarize it. And if there's anything unclear based on those two videos, then you need to let me know. All right. So, moving on. First game. When using three rotation parameters, a problem is singularity, physical interpretation of parameters. The usage of three parameters is limited to small rotations only. Small rotations like linear rotations, or something that it's limited to, let's say, plus minus 10 degrees. So one only is correct. But which one is correct? In class quiz is going to be on. Hold on. I think, yeah, it's going to be on right now. So please lock yourself to Socrative. And again, the way you can log into Socrative is that I see that there is already 6 students in the system. And I see that the answers are already, I'm collecting answers. Okay, so I'm kind of thinking that you still guys are alive, and I have no problem in my settings. It's just that you're not willing to communicate with me. I'm just checking my emails. No emails there. Yep. Yep. Okay. All right. So Socrative is here, and I see that I think that I have 19 participants in this stream. I think so. That I cannot be 100% sure about that, but I think it is 19. I have two different numbers here, 13 and 19. Anyway, so where's my OBS? Here's my OBS, and this is my Socrative. So game is on. So what's going to be the success rate? 100? At least this time, I think there may be 100 already, because um, we kind of have a small group of students, and I somehow am feeling that you guys are one of those super clever ones. So probably we're gonna score 100% number of times in this course. Maybe that's what I'm hoping. This is what I'm dreaming. So not just a single time, but the number of times. And we'll see that. We'll see that. Now I'm really convinced that you guys are not able to use this chatting window, because even when I said that the game is on, no answers or no guessing. What's the success rate? Okay, so how many answers I have? I have 17, 17, and based on the number that I'm looking at from my YouTube studio, it should be 18 views. So I'm pretty much done. All right. So let me take myself to this window here. So 18, now is 18. So I think this is it. So each of you already answered. So the results, and the results are this. Oh, I'm relieved. I'm relieved because I thought that, we're going to score 100% in a first question. First question, that would be unprecedented, something that, no one would believe that we're scoring 100% in the first question. But thanks God, there's a one incorrect, and it wasn't me. It seriously wasn't me. My hands were all the time visible. So it was not it wasn't me, but somebody else. Okay. And again, I got some kind of error message that the streaming is not smooth. And now I guess it is back smooth. Okay. Ooh, close case. This would mean a lot of dancing and singing if we're going to score 100% every single time. And of course, the problem is singularity. Singularity is a problem here. All right, so let me take that off. And let's moving on. So we still have a couple minutes time. So let's open the second way to describe the rotations. And now what will happen, or what follows, is that we are no longer using three parameters to describe three rotations. Why? Because whatever we do that, we have this problem of singularity, inability to describe the rotations correctly. So that's what can happen to us. And we cannot fix it by changing the order of rotations or changing the axis of rotation. That makes no difference, really. So that's not the solution. But the solution is that we're using four parameters. Four parameters. That this is conceptually like, what? Four parameters. So how is it even possible to do that? And I think the easiest way to do it is by we first take a look at the Rodriguez equation. And here are the questions. Explain the concept of Rodriguez equation. Explain the concept of Euler parameters, which is a extension of Rodriguez equation. And remember, Euler parameters and Euler angles, completely different story. No relation whatsoever. I mean, there is a relation. Of course, you always can build a relation, but conceptually, very different stories. Very different stories. In three-dimensional case, body orientation can be defined by using Euler angles and Euler parameters. Explains the concept of Euler angles and Euler parameters. How these two methods are different. Well, they're very different, as you will learn very, very soon. Okay, but with that, let's get started from Rodriguez equation. And in Rodriguez equation, I need to get a little bit of like tools to help my explanation here. Let me see. I think, look at this pen. So it was hiding here all the time. My mistake. Let me see if this works. Oh, it's not working. Okay, I think the battery is dead. Let me charge this so I can start using the pen. So it was all the time too close to me. Too close. Okay, this is back in live momentarily. All right, but what I need to explain this. Okay, I think the two pens will do it. All right, so concept of Rodriguez equation. Rodriguez equation, in the beginning, we need to take a look at that vector r. The vector r that is, let me see if my pen is already operating, the one that is shown here. All right. So I will have vector r. Let's say that this is a vector r. This pen is a vector r. Now this is a vector that is located in the space. What I will do is that I will take this vector and I will change its orientation in the space. So it will have initial configuration like this, and then the final configuration like that. And I'm going to build the relation between the final and original configuration of this vector. And what will follow as a consequence of describing this relation between the final and original configuration is a 3x3 rotation matrix. And this is going to be mathematical, a little bit involving. But again, in this course and other courses that I'm teaching, we really don't care that much about the details, mathematical details. We care more about what's the concept behind. So now, again, remember, we have original configuration, final configuration. The vector length, obviously, is with no changes. And I can see my camera is getting confused when I'm having a pen in front of me. All right, so what I will do then is that I will introduce additional vector that is unit in length, unit length vector v. And I'm going to attach this unit length vector to origin of my vector r. And now I'm going to do this changing of orientation with help of this unit vector v. And I'm going to find the rotation and configuration between the original and final configuration by rotating this unit vector v, like this. So now we will do the same thing like I did it before. But now this rotation is this with help of vector v, and the vector v is unit in length. All right. So whereas that I can see this vector v, which is unit in length, is this one here. Remember, this is the configuration. So I have this original vector here, and then I'm going to add dots. I'm going to change the color to make this absolutely visible for you. And then we're going to attach this unit length vector v that is in the same point here. They're getting started in the same point. Now, rotation will then take place around this unit vector v. How much is a rotation? That's going to be the amount of theta. All right, I'm going to have a better assisting devices with me next week, so I'm going to repeat the whole story, but that's how it roughly goes. Okay, now what we're going to see is that this is going to be the final outcome. So vector r bar is the final outcome. And now, like I say, we will build the relation between the final and original configuration, and that's going to give us a description of rotation matrix. That's how it goes. And I see that kind of running out of the time, so we'll see how well is this explanation now. Now, to do this mathematical relation between the final and original configuration, you need to use a series mathematics, series algebraic relations. And using this series algebraic relations, you can find this where the originally this r is ending, excuse me, r here, where the r bar is ending. So they are q and p. And basically what I wanted to do here is that I wanted to find this vector here. And this vector, I can find it out by introducing p1 and p2. Don't put much of an attention to these details. This is more like a details. Keep the big picture in your mind all the time. And we can describe this b1 and b2 by first looking at what is their direction and what is their length. I need to know these two information to build the vector, direction and a length. So that's what I can do. And like now, if I really cut the corners, I can build the b1 and b2 like it is shown here. And this is going to be my 3x3 rotation matrix. Very, very confusing, super confusing. And I was jumping kind of the final result here. But if moving slowly, if looking at, how is that these b1 and p2 can be actually built, these two slides are explaining that. So b1, first is length and the direction. And as I'm really running out of the time, this explanation will be available next week. But again, I don't think it is really important explanation because this is more like mechanical thing you can learn by if you're very much fascinated about the mathematics. And if not, that's okay. So not a big problem. But I'm building the description of vector b1, length and the direction, p2 length and the direction, and then I'm going back here. Then I'm summarizing p1 and p2, and I will get this difference here, this delta r. This delta r that can be used from original configuration to final configuration. So if I have these missing b's between the final and original, then that's going to be my rotation matrix. And again, no worries. I will explain the details to you next week a couple more times. But now take a look. How is it then? This is the kind of like the mapping here. And what I can do for this mapping, I got the information that I need to restart my computer, but I'm not planning to do it right away. So this is my delta here, delta r. and it's explained it in a way that I have my, let me go here. I must still have my final configuration involved with. So the final configuration is here. So what I will wanted to do here eventually, I want to get rid of this final configuration, and I will take it as a separate part of my notation. And this is what is left before that final configuration. That's going to be my rotation matrix. And now there are notations that you may not be aware of. There is, first of all, well, this is, I'm sure you know this guy here. This is identity matrix. It's going to be 3 by 3 identity matrix like this. And again, don't get scared. You know, this is not this bad story at all. You know, this was just, you know, waking you up. And the next week we're going to go back to the pleasant story. So no worries. And then this skier matrix here is this unit length vector V here, the one that is here, but it's in a skew representation of that vector. What is the skew representation? That's a skew representation. So you can take any vector you want, and you can express this vector by using a matrix notation like shown here. You simply, you know, this is the matrix A that I'm expressing by using the skew representation. So I'm simply relocating its component to 3 by 3 rotation matrix. How? Well, this first component it finds its way to here in a minus sign, and then here in a plus side. Then 2, it's going to be here, and it's going to be, so instead of using this kind of cross product relation, you can use this in a skew symmetric form. And when you're using that in a skew symmetric form, this is how it looks. So this is my V in a skew symmetric form. This is a V power 2, and again, skew symmetric form. And this is it. This is it. All right, back to the physical interpretation. So what is that I have here? Now, this is my, when you do it, by the way, when you do the math here, when you're multiplying all these components together, you end up to have a 3 by 3 rotation matrix. But what are the rotational parameters this time? What are the parameters included here? Well, vector V. That's the parameter here. Vector V, remember the vector V consists of 3 components, V1, V2, V3, which is this guy here. Remember, this guy that was used to introduce this rotation. That's the vector V in the skew symmetric form. So that's going to be my first 3 parameters. 3 parameters. One more parameter is needed, and this one more parameter is this angle theta. That's it. Now I have 4 parameters, and you can tell that the physical interpretation is not easy in a general case. But once you follow the story, when everything gets started, then it makes sense to understand it. It's understandable in that perspective. Okay. All right. So I say that it's time to close today. But here are the 4 parameters. 3 variables in V, 1 variable in angle theta. And the big question is that now, is it describing the 4 different rotations? No, not the 4 different rotations, because remember the one sentence that I used in the beginning. I said the vector V is unit in a length. So that's constraint. So I'm forcing the vector V to be unit in a length. So there's going to be 4 parameters, 4 variables, 1 constraint. And the constraint is associated to vector V. And with that, we're going to close today. And I guess I'm seriously thinking that there is something wrong in my chat window, because no communication today. Absolutely no communication. So we'll check my settings next time, and I will get back to this Rodriguez equation, and I will explain how is Euler angles and Euler parameters next time. And next time, make sure that you have the extra 45 minutes after this lecture. So I'm going to first explain these technical things, carrier cancelling, what follows. All right. So exactly on time. So it's 9:45. So let's close today's lecture, and see you guys around, which I think that is not going to happen because I'm again here in my basement office, but see you guys next week.